this is section 6.1. We're going to fold this in towards the center. I'm going to write it up here. 1.6. This section was at the beginning of the school year, but it didn't apply to anything that we were doing. This is the perfect place for it. That's why I moved it over here. We're looking at today is polygons. Polygons are...
Why are you recording?
A closed figure. Composed of line segments. So if they're not lines, for example, curves, then it's not a polygon. If it's not closed, sort of like I was mentioning with the triangle, that if it's not long enough, then it can't be called a triangle, can't form a triangle, it won't form a polygon. If we look over here, we need to know the names of some of these polygons. That's why I gave you this sheet of paper. What is the name of the polygon with 3 sides? A triangle. 4 sides.
Square.
That's a very specific 4-sided figure.
Rectangle.
Quadrilateral is in general. So don't forget like a trapezoid or a rhombus that are also quadrilaterals. A 5-sided figure. Pentagon. Six-sided? Hexagon. 7-sided? Heptagon. 8-sided?
Octagon.
Octagon. 9-sided? Nonagon. 10-sided? Decagon. I forgot to put 11, sorry about that. An 11-sided figure is a hendecagon. Hendecagon. There we go. Hendecagon. 12-sided? Dodecagon. And then in general what we say is n-gons. And that's usually when we don't know the sides or it's really big. For example, 35. We call it a 35-gon. Okay. On this other side, we have concave and convex. The easy description for concave is that it actually has a section where it caves in. So if you look inside, there's 2 vertices can connect outside of the interior of the polygon. So what they're saying is that if you connect 2 sides, it would be in the exterior of the polygon. And that's great and all, but it's easier to identify if you just find the part that it concaves. It caves in. Any polygon that caves in is considered a concave polygon. And that's all you're looking for. The convex then doesn't do that. And what it says is any 2 vertices only connect with within the interior of the polygon or the side of the polygon. So let me just give you this instance. This would be on the side. And then if we try to connect these, it would be on the inside. But that's great and all, but the easier way to identify them is that if you just see a cave in, it's concave. And then the other one would be convex. We're going to go down here to the regular, irregular. What it means to be regular is equilateral. That means all the sides are equal. And equal angular means all the angles are equal. It has to have both conditions. If it doesn't, or it doesn't have any notation, it's irregular. So if we take a look inside, the polygon is convex and sides are congruent and angles are congruent, then it's regular. See here how we have no notation? It has to have that all the sides are equal. But that's not good enough. It also has to say that all the angles are equal. So on here, I'm going to make this notation. So don't forget, all the sides are equal and all the angles are equal for it to be regular. All the sides, making it equilateral, and all the angles, making it equal angular, that make it regular. All the sides equilateral, and all the angles equal angular. Without that notation again, we don't have enough information and cannot call it regular. Irregular is anything else. Okay. Finding the perimeter. Don't forget that when you're trying to find the perimeter, what you do is add all sides. Let's take a look inside. To find the perimeter of a polygon, if it's on the grid, we just count. Let me make letters for the vertices, just so it's easier to identify. For the segment AB, it would be 1, 2, 3, 4. But then from BC, is not on the grid, so we have to do the distance formula. So BC, I'm going to write the order pairs up here. This is 3, 3. This one is 1, -3. Just to remind you, the distance formula was x2 minus x1 squared plus y2 minus y1, close the parentheses, squared. So we're going to do the square root of the x's first. Which one you call 1 and which one you call 2 really won't change your answer. So I'm going to do 3 minus 1. 3 minus 1 squared plus. Then your y values. 3 minus -3 squared. Gives you the square root of 3 minus 1 is 2 squared plus 3 minus a -3 is 6 squared. The square root of 4 plus 36 is the square root of 40. So you could write the decimal approximation, but remember, I don't grade you on that. I grade you on that square root, but I just wanted to show you what it gives you, which is 6.32455, and it's irrational. That means that the decimal will never stop and it doesn't start repeating. Why does that matter? There's no way to count it, this value, and you had to do the distance formula. Then you have DC. Since it's on the grid, we can count it. 1, 2, 3, 4. That means that for AD, we're going to have to do the distance formula. The order pair for A is -1, 3. And for D, -3, -3. So we do the x's first. -1 minus -3 squared plus And then the y values, 3 minus negative 3 squared. When you simplify that radical, 1 minus negative 3 gives you 2 squared plus 3 minus negative 3 squared. Just 3 minus negative 3 is 6. The square root of 4 plus 36 is equal to the square root of 40. The perimeter then, and you have to add the sides. I'm going to put P for perimeter, 4 plus 4 for the integers. And then I'm going to put plus 40 plus the square root of 40 as the radicals. Remember, I don't want the decimal approximation, so how would you simplify this? 4 plus 4 makes 8, and there was 2 of the square root of 40s. This is a skill that you would need for your Algebra 2 class when you have to solve for quadratics. And that's why I wanted to present that here.